Alright, let's look at the homework 16.3, problem number 4. Alright, so we have a vector field given here, and which is 2xy comma x squared. Let's say this is conservative, right? So we're going to say this guy right here is going to be our P, and this guy right here is going to be our Q, right? Then if you take the partial derivative of the first component, which is P, with respect to y, you're going to get 2x, right? And if you take the partial derivative of the second component, which is q, with respect to x, we're going to get 2x, right? So you can see that these partial derivatives match up. So therefore, we know that the original vector field is conservative, right? So vector field is conservative. All right, so since it's conservative, we should be able to find the associated potential function, right? So let's find that. All right, so we know that the partial derivative of the potential function, little f, with respect to x, has to match p, which is 2xy. Right, so we can take the antiderivative to find f. So f is going to be antiderivative of 2xy with respect to x, right? So we're going to get the antiderivative of 2x will be x squared, and y is just a constant. So we have that. And then you might have plus some constant, but the constant could be a function of y. So I'm going to put the g of y. All right, then also we have to make sure that the partial derivative, this potential f, with respect to y, has to be equal to q. So let's do that. So take the derivative of that with respect to y would be x squared. And the derivative of g of y with respect to y would be g prime of y, right? So you can see that this is going to be equal to x squared, right? So which means that g prime of y has to be equal to 0 because there's nothing else. So we can take the antiderivative of that with respect to x to find g. So g of y is going to be some sort of constant, so I'm going to call it k, right? All right, so therefore, hold on a sec. All right, then potential is going to be, all right, we know that here x squared y, and the g of y came out to be a constant, so we have that. All right, so let's answer a question here. All right, so explain why integral vector field f dot the dr has the same value for all three curves. So we are talking about, going from here to there. You have here's a curve 1, here's curve 2, and a curve 3. All right, so since this vector field f is conservative, it's going to be independent of paths. So no matter what path it takes, it's going to have the same value as long as starting point and the ending point are the same. So we can see that, let's see. If you read it, let's see this one. The vector field is conservative and all three curves have the same initial and terminal points. So this should be the answer, right? So let's check the answer, right? Submit for testing. All right, I came back and looks like we got part A correctly, right? And part B, what is this common value, right? So we can use the fundamental theorem here, right? So we have an integral, right, over any curve. So I'm going to just call it C, right? Then capital F dot dr, And since this is a conservative, we can rewrite this as a gradient of its potential function dot dr, right? And this is going to be equal to, so you have a f, and then we plug in the ending point first, so you can see that the ending point is going to be 3, 2, right? So we're going to put the 3, 2, and then minus, then plug in the initial point. So initial point is 1, 2. So we're going to put the 1, 2. Right? So what you get is going to be, you put 3 here. 3 squared would be 9 times 2, so it's going to be 18. And you can put plus k if you want. It's not going to really matter. Minus, right? Plug in 1 here. 1 squared times 2 is 2 plus k. Right? So you can see that k really didn't matter because they're going to cancel out. So this is going to come out to be 16, right? So the common value would be 16. So let's type it in, 16 here. All right, then submit for testing. All right, it came back and looks like we got this one correctly. All right, that's it. I hope that this was clear.